we actually implement semaphores? And we'll talk about a couple ways. The big thing is that weight and signal themselves need to be atomic. In other words, they have to, as you say, check the variable to see if it's non-zero and decrement it. And they have to do that without somebody else starting their check and decrement, because we can get into the same problem that we got into with the bank balance. So we have a couple schemes. We can implement them in a kernel's supervisor call, which has the advantages once you get in the kernel, no interrupts can happen, only the kernel is running. So that's a very simple way to guarantee atomicity from the user's program point of view. We can add an instruction to the hardware, which I'll show you in a second. Or there's actually a clever way just using reads and writes to memory, but it's actually never used in practice. So it's usually one of these first two implementations, a kernel call or a special test and set instruction. So the kernel call looks very simple, right? I mean, here's the wait thing. You can see it going off. We put the address of the semaphore variable, so we don't actually hand in the value of the semaphore. That'll be up for the kernel to check. What we do is we say, here is the thing we put into R0 is in fact the address of the semaphore. The kernel then uses that address to access user's memory, checks the value. If it's less than or equal to 0, in other words, we need to stall, you can see it backs up, and so that when we re-execute the user program, we'll re-execute the wait supervisor call again, and then we go call the scheduler saying, I'm going to go to sleep, wake me when somebody has put something into this, incremented the semaphore. And down here you can see the signal, which works very much the same way. We pass in the address of the semaphore, increments it, and then does a wake up on that address. So remember the sleep and wake up mechanisms that guarantee in a time sharing system that we don't bother running you if there's really no sense. But the big thing is that this notion of checking the semaphore and then and in this case decrementing it. Okay, because this is in the kernel, we can't get any interrupts between this check and this decrement. So that's what I mean by them being atomic. If I execute the check, I can guarantee that I'm going to decrement it. Okay, so in this particular case, the semaphore should never get below 0, right? Because if it was equal to 0, I should never decrement it. There's no accidental somebody checking it and then later decrementing it, thinking it was still non-zero. I mean, if I check it, then I'm going to decrement it. Okay. Another way, the test and clear, where the atomic piece of the operation you can see down here, which is basically I get back the old contents of the memory location and I set it to 0. And that turns out to be enough to be able to implement a very simple binary semaphore. And once you have a binary semaphore, something you can use for mutual exclusion, then you can have a critical section of code that goes off and takes FFTs or whatever you want for this on the semaphore. You can implement a much more, an integer semaphore that involves actual incrementing and decrementing, so long you're guaranteed that the sequence of instructions that you're using to manipulate the semaphore is guaranteed to be atomic, that only one process can be in this code at once. So test and clear.